Hi everyone. In this video, we are going to derive an expression for rotational energy. In our last video, we derived an expression for moment of inertia, I is equal to mu r square. So, while considering that topic, we were discussing about rigid rotor and all. So, here also, in this case, we are continuing with all those same consideration. So, suppose we are having a diatomic molecule, that is basically our rigid rotor itself, and it is rotating about its center of mass. So, rigid rotor will be something which is like this, and it is having a bond which is connecting the two masses. And now this is rotating about its center of mass, and you know center of mass will be shifted towards the one which is having higher mass. From this picture it is obvious that this one is having more mass. So it is rotating about an axis in the center of mass with a velocity, because it is rotating, it will be having an angular velocity, and let that angular velocity be omega radians per second. So from definitions you can write an expression for its angular momentum. So the angular momentum of this rotor molecule will be given by L is equal to I omega, that is moment of inertia multiplied by the angular velocity. We have discussed about it in the last video. So now the angular momentum, we know it is a quantized quantity, and it is given by an expression L is equal to root of J into J plus 1 H by 2 pi, where J, we know this is the rotational quantum number, and J can have the values. J can be 0, 1, 2, 3, etc. It's the rotational quantum number, and this is a quantized quantity. So let's give number to the equation. Let this be equation number 1, and let this be equation number 2. And here H, as we all know, it's Planck's constant. So now the energy of the rotating molecule, this molecule, will be given by half I omega square. Ej be the energy of that rotating molecule, that is equal to half I omega square. So now we are going to substitute omega. Now we are going to find an expression for omega from this equation number 1, and we are going to substitute in this energy equation. So when I am rewriting this equation in terms of omega, our equation will be omega is equal to L divided by I. This will be our equation. And in the energy expression, we are having omega square. So upon squaring this, you will be getting omega square is equal to L square divided by I square. And now I am going to substitute this omega square instead of this omega here. So the expression of energy will be like half I L square divided by I square. So upon cancelling these I and rewriting this equation, you will be getting Ej is equal to L square divided by 2I. Let this be our equation number 3. So now I am going to substitute this equation number 2 in equation number 3. So the expression for the allowed rotational energies of a rigid diatomic molecule will be like this expression. This will be equal to h square divided by 8 pi square I of j into j plus 1. Upon squaring this L, upon squaring this root will be getting cancelled, and here you have to square. So h will be h square, and this 2 will be 2 square, and pi will be pi square, and 2 square will be 4, and here you are having a 2. Upon multiplying you will be getting 8. So your expression now changed to this one. This is the expression for allowed rotational energies, and let it be 4. And you know, J is a rotational quantum number which may have the values of 0, 1, 2 and 3. So in the earlier, when we were discussing the molecular energy level diagrams, I have discussed molecular energy level diagrams in Born-Oppenheimer approximation. So upon discussing that, we have studied this diagram. So whenever a molecule in a particular rotational state is absorbing microwave energy, there will be transition from lower energy level. Suppose if the molecule was the ground state, let the molecule be in this state, and after absorbing it is getting transported to this level, this rotational level. So you will be having a gap, energy gap Ej or delta E, let it be. So to calculate this delta E, what you will be doing is, I'll write it here. So to calculate that delta E, suppose let the lower J be J, suppose the higher J be J dash, and the higher and this lower J be J. So when it is going to emit some radiation, means it is going to jump from this higher level, energy level, to lower energy level. So this delta E can be found from Ej dash minus Ej. So what you have to write is, you know what is Ej, the basic expression. This is the expression for energy. So now what you have to find is delta E. So to find delta E, you have to see del Ej dash minus Ej. So to find Ej dash, you have to denote this J by a dash term. So our expression of delta E will be like this: h square by 8 pi square I of j dash plus 1 minus this minus term, then Ej. It will be h square divided by 8 pi square I j dash. Here we are considering j, so j into j plus 1. So here you are having these terms as common. So upon taking the common terms outside, our expression of delta E will be h square divided by 8 pi square I j dash plus 1 minus j into j plus 1. So we are done with this. Then in the rotational spectroscopy, wave number means energy divided by Hc. So wave number, or we can say wave number, is represented by this mu bar. That is equal to, we know, delta E, energy gap divided by Hc. This or wave number of an absorbed radiation or an emitted radiation as a result of the transition between energy levels, as we have discussed, whenever this kind of transition from lower state to higher state is happening. So that is the energy, this kind of transition between energy levels is that we will be considering those kind of transitions normally. So it will be convenient to consider energies in the same unit. That means what you have to do is this equation and the equation number 4 should be having a same unit. So what we have to do is we have to just divide this equation number 4 with hc, where c is our velocity of light. So upon division, what you will be getting is this equation will be changing to let's denote another term, or let this be the rotational term. This kind of em rotate, I'm writing this in a special case Ej is equal to this Ej divided by hc. So this will be, let's write this equation, h square divided by 8 pi square I divided by hc of j into j plus 1. So upon cancelling, you will be getting h divided by 8 pi square IC of j into j plus 1, that much centimeter inverse. So now you are having energy term and this wave number term, this both in this is in centimeter inverse. So you are having energy and wave number term in the same unit. So basically why you have divided it is to make everything in the same unit. So this term, this new term is known as our rotational term. So this rotational term can be expressed in another way, like putting an constant or something for this bigger expression. So you will be getting a small equation which is handy to deal with the problems. So this Ej you can write like b j into j plus 1 centimeter inverse, and this b is this whole term, this h divided by 8 pi square IC. So I'll write it once again. B is equal to h divided by 8 pi square IC, that much centimeter inverse. This is the rotational constant. This B is rotational constant and it is characteristic of each and every molecule. So if you are considering an HCl molecule, it will be having its own rotational constant value. If you are considering an NO2 molecule, if you are considering, so depending upon the molecule, there will be different rotational constants. So defining B in the above manner, you can write this equation of Ej in another terms. So equation of Ej in terms of this rotational constant be looking like this: BHC j into j plus 1. So when you are substituting the j values, if you are substituting like j values means 0, 1, 2, 3 etc. and all, you will be getting the allowed rotational energies of a rigid diatomic molecule. That means if you are keeping the value of j as 0, like the molecule is in ground state, so you will be, if you are keeping this as 0, you will be getting energy as 2 BHC. If you are keeping it as 1, you will be getting the value, the energy value as, if you are keeping 0, you will be getting this one. If you are keeping 1, you will be getting 6 BHC. If you are keeping it 2, you will be getting 12 BHC. Then for 3, you will be getting 20 BHC. For 4, you will be getting 30 BHC. So from this expression, you will be getting the energy values of molecule in different rotational levels. So this is all about the derivation of finding expression for rotational energy. In the next video, we will be discussing the selection rules for rotational transitions in detail. Thank you.